I will give a quick introduction. Hi, everyone. I'm delighted to introduce our speaker, Dr. Michael Hope today. Michael is an assistant professor now at Warwick solid-state NMR group, and he worked with Professor Claire Gray at Cambridge during his PhD, and then worked with Professor Lyndon Emsley at EPFL during his postdoctoral, where he was also awarded the Marie Curie Fellowship. He's an expert in using solid-state NMR to understand materials at the atomic scale and design advanced materials for energy storage, such as batteries and solar cells. And today he will be sharing with us how to use DNP on metals. And feel free to start when you're ready, Michael.
Thank you very much for the introduction, and thank you for the invitation to talk today. It's a real pleasure as someone kind of outside the EPR community to be invited to share my work, and hopefully we'll find something that's of mutual interest. And so, as you mentioned, I'm going to tell you about endogenous dynamic nuclear polarization using both high-spin metal ions and bulk metals. So, as a motivation to start with, we can talk about why NMR is clearly an inferior technique to EPR. And of course, this relates to the sensitivity, which is always a problem for NMR. And so our sensitivity depends on our polarization, which depends on the gyromagnetic ratio, the magnetic field, and the temperature. And so if we think about doing proton NMR on, say, a 600 megahertz spectrometer, even at a low temperature of 100 Kelvin, we only have around a polarization of 0.02%. Whereas if we think about electrons under the same conditions, the gyromagnetic ratio is almost 3 orders of magnitude bigger, and so we have a polarization of around 12%. So that's what's shown in this figure on the right, showing polarization versus temperature on a log-log scale, both for protons and for electrons. And so in dynamic nuclear polarization, we transfer the polarization from electrons to nuclear spins in order to boost our sensitivity in our NMR experiment. So today I'm going to give you 3 examples of my work using DNP. The first 2 focus on high-spin metal ions, in particular gadolinium, both in cerium oxide and in indium hydroxide. And then we'll switch gear a little bit and talk about using lithium metal as the polarization source in DNP. So if we start off with the high-spin metal ions, the first question is really, what do I mean by endogenous? And so actually the way DNP is typically done is we add our source of unpaired electrons as typically an organic radical dissolved in a glass-forming matrix that we then wet our solid sample of interest, represented here. And so what this means is our polarization source is outside of our sample. And so this results in some inherent surface sensitivity, some surface selectivity, which in a lot of situations is very beneficial, but it's not necessarily the best way of doing things if you want to look at the bulk. And how much bulk signal you get from this approach really depends on how efficient your spin diffusion is. We can contrast this with endogenous DNP, where our source of unpaired electrons is internal to the material. So this is shown as an example here with some sort of paramagnetic dopant, which is often a high-spin metal ion. So it's worth highlighting that this approach, the endogenous approach, has really been pioneered by the group of Michal Lesks and the Weizmann Institute. And in fact, these nice figures were taken from one of her reviews shown below. Okay, so if we're doing endogenous DNP with using high-spin metal ions, we're typically using the solid effect. And so I'm going to take a little bit of time to explain roughly how the solid effect works. And to understand the solid effect, we need to consider a 2-spin system, 1 electron, 1 nuclear spin, which results in these 4 levels. And so here, the lower levels have the electron spin down, and the upper levels have the electron spin up. And then the left-hand levels have the nuclear spin up, and the right-hand levels have the nuclear spin down. And so that results in the splitting by the electron, Larmor frequency, this big splitting, and then this smaller splitting by the nuclear Arnold frequency. In the solid effect, we use applied microwaves to drive either the zero quantum or the double quantum transition in this four-level system. So what that does is it simultaneously flips an electron and a nuclear spin. And we can see what that does to the populations. So here, the population of each level is represented by a circle. The bigger the circle, the larger the population. And so at thermal equilibrium, we have a large electron spin polarization. So there's a big difference between the bottom and the top. But we have a small nuclear polarization. There's very little difference between the right and the left in either of these levels. When we saturate one of these transitions with applied microwaves, that acts to equilibrate the populations. So we go from a big and a small circle to two medium circles. We can see what that's done is it's reduced the electron spin polarization. So now there's a smaller difference between our upper levels and our lower levels, but it's increased the polarization of the nuclear spins. So now there's quite a big difference between the right-hand side and the left-hand side, both in the upper levels and the lower levels. And this polarization we develop here, if we saturate the zero quantum transition, is opposite in sense to Boltzmann. So by Boltzmann, we'd expect the lower energy to be higher populated than the right. And so this is a negative enhancement. It's in the opposite direction to the thermal polarization of our nuclear spins. If we saturate the other transition, the double quantum transition, now we can see analogously, we've again reduced the electron spin polarization, so a smaller difference between the bottom and the top. But we've now got a positive enhancement of our nuclear polarization because we now have more population on the left than on the right. So more population of the lower nuclear level than the upper nuclear level. Okay, so that's very briefly how the solid effect works. If we want to use the solid effect, there are a few requirements to get efficient DNP. So basically, we need to effectively saturate those resonances which are only weakly allowed. So to do that, we need slow electron relaxation and we need a narrow resonance. If we're thinking about metal ions, if we have any spin-orbit coupling, well, A, that causes rapid relaxation, so it's hard to saturate those transitions. And we also deviate from the free electron G value, which means that probably on our DNP system, we're not going to be able to hit the transition anyway. So what this means is we need metal ions which have quenched orbital angular momentum. And there are some classic examples of this. You can have a D5 system, such as manganese 2 or iron 3, where you have a half-filled set of d orbitals. You can also have a D3 system, such as chromium 3, where you have a half-filled T2G set if you have octahedral symmetry. Or you can have a half-filled set of f orbitals, so F7, which is gadolinium 3+. So what all of these have in common is that they have no orbital angular momentum because they're half-filled, but they have high spin, so they have a spin of greater than a half. What this means is they're subject to zero field splitting. So for an NMR audience, we can think about this as being analogous to quadrupolar coupling. And it's caused by a non-cubic charge distribution, resulting in an electric field gradient. We typically only concern ourselves with the central transition because the satellite transitions are broadened to first order. The central transition isn't, it's only broadened to second order. So that means that our central transition is narrower, it's easier to saturate. And the width of this central transition is proportional to the zero field splitting d squared and inversely proportional to the applied magnetic field. What this means is that if we want to use DNP of high spin metal ions, we need a highly symmetric metal environment in order to minimize the zero field splitting to give a narrower line width that we can more readily saturate. So this is an example of this design criteria. This is work from Lynn Lensley's group at EBFL that was being done by some of my former colleagues when I was in the group. And they were looking at organic complexes of gadolinium. So these are various complexes that are quite symmetric. And what they did was they measured the zero field splitting, which is shown in these blue bars, and they measured the proton DNP enhancement, and you can see that the smaller the zero field splitting, more or less, the larger the enhancement you get. If you plot that out a little bit more quantitatively, if you plot the DNP enhancement against the zero field splitting, you can more or less fit it with a 1/d² dependence. So for instance, this prize-winning complex, this gadolinium TPA-TCN, you get a proton enhancement of around 38. And if we compare that with something like gadolinium-doped, which was kind of the state of the art before this work, very commonly used contrast agent in MRI. Here I'm showing the, I think it's the W band spectrum, and you can see that the TPA-TCN has a narrower central transition line width, and so that's what results in this higher enhancement. So when we were discussing this in group meetings, one of the questions I had was, can we ever make these complexes symmetric enough? So for an organic gadolinium complex, you typically have 9-fold coordination. And from a symmetry perspective, there's no way of having a cubic arrangement of 9 ligands. You can't have the zero field splitting be zero by symmetry. Whereas I come from a more inorganic kind of materials background, and there are lots of examples of crystalline solids where that have high symmetry metal sites. And so, for instance, cerium oxide, you can dope gadolinium onto the metal site. This is cubic, and the zero field splitting is 0 by symmetry. And so we were interested to see, can we use DNP based on gadolinium, and is that going to be more efficient due to this higher symmetry? So here I'm going to show you some oxygen DNP of gadolinium-doped ceria. So cerium itself has no NMR active isotopes, and so we're going to do some oxygen. Oxygen has a low natural abundance of 0.04%, and so this sample is actually oxygen enriched. So enriched with 17O, and this is on a 9.4 Tesla DNP system operating at 100 Kelvin. So what I'm showing here is the oxygen spectrum with no microwave irradiation. And then if we turn on the microwaves, we get a massive boost in the NMR signal. So if we zoom out, you can barely see the microwave off signal. And so we characterize this by an epsilon factor. That's the ratio of the microwave on signal to the microwave off. This is what I'm going to call the enhancement. And we're getting an enhancement of about 650. The peak enhancement is slightly less. That's because the enhanced spectrum is actually broader. It's broader due to radiation damping. There's actually so much magnetization that it couples to the coil and causes relaxation. But that's kind of a side point, really. So this is obviously was very exciting when we managed to get this. But it's cheating slightly. So obviously oxygen has a lower gyromagnetic ratio than protons. So it's not really directly comparable. But if we want to just compare the amount of magnetization we've generated here, so if we rescale it to protons, it would still be a factor of 88 equivalent for protons. So this is obviously higher than 38 that we got for those best organic complexes. And so at this point we thought, okay, so the higher symmetry of this crystalline lattice means that we can get more efficient DNP. So let's see whether that's the case. So the next thing we explored was the effect of concentration. And in fact, we started at this end. So we started with 1% of gadolinium doping and progressively lowered the doping. And that spectrum I just showed you was for 0.01% gadolinium. And so you can see that the enhancement decreases monotonically if you increase the concentration. To understand that, let's have a look at the EPR spectra. So these are X-band EPR spectra that I've then integrated to, so they're kind of more familiar for an NMR audience. And what you can see is that the higher the concentration of gadolinium, the broader the resonance, primarily due to dipolar coupling between the gadolinium ions. It's worth also mentioning that because gadolinium is 3+, whereas cerium is 4+, if you dope gadolinium, you have to introduce oxygen vacancies to balance the charge. the presence of oxygen vacancies will break the cubic symmetry, so that could introduce some zero field splitting. So that may be a factor, but I think it's predominantly the dipolar coupling. So this makes sense. So the broader, the higher the concentration, the broader the EPR line, the less efficient the saturation, and the worse the DNP. So that's all very consistent. What's interesting, though, is even at the lowest concentration, we're reaching a kind of a limiting line width that has some structure to it. So to understand that, we need to actually fit these spectra. Unfortunately, this was done back in the 60s, and so we can just take these previously determined values. The important thing here is, although there's no second-rank zero field splitting, so second-rank ZFS results from a charge distribution that looks like a d orbital. That's zero by symmetry, but there is fourth-rank zero field splitting. So that's a charge distribution that looks like a g orbital. So that's this B4 parameter here. And in fact, there's also a little bit of sixth-rank zero field splitting. And actually, when I then compared these EPR spectra with some of those organic complexes, we've got a central transition line width here of around 500, that's equivalent to if you had a zero field splitting, second rank, of around 500 to 600 megahertz. So it's actually, we have a very similar central transition line width here to the organic complexes. And so the first kind of sort of take-home message for us was that as a design principle, cubic symmetry is not enough to give optimal DNP, because you then become limited by higher rank zero field splitting terms. And in fact, for a material like ceria, the very rigid, well-defined charge distribution that can give us a vanishing second rank actually probably contributes to giving a large fourth rank. And so really what you want is a spherical charge distribution, but that's much harder to achieve. And so there's some interesting work, for instance, in fullerenes. The second thing to understand is, well, why, if the central transition line width is more or less the same between the organic complexes and this crystalline material, why is the DNP 3 times better in this case, or at least double? And so this actually arises from the fact that in this inorganic solid, you have a very rigid lattice, and that results in slower electron relaxation as compared to the glassy organic solvents that are used for the organic complexes. So that was kind of another design principle that if you can have rigid materials, you can actually slow down the relaxation and improve the DNP performance. The fact that we have a rigid lattice also means that we don't have a hard temperature limit. And so unlike the glassy solvents, which melt, ceria is a solid up to several, or at least a couple of thousand degrees. So we can explore the temperature dependence of the DNP. So what I showed you before was down at 100 Kelvin. But if we go up in temperature, our enhancement decreases. That's because our electron relaxation gets faster. But we can still get an enhancement of 150 at room temperature. Also, because we're not limited by sort of how, so when you do DNP, it's a trade-off between applying more power, but not heating the sample too much. If you're heating the sample anyway, it doesn't matter, so you can apply more power. And so these red points here, I've doubled the microwave power, and okay, you can't sort of, you can't win, you can't get a higher enhancement because you've also heated the sample. But at room temperature, you can now get an enhancement around 320. And in fact, we went even further. Should mention that the probes are not rated above room temperature, but we managed to get it to work up to about 100 Celsius, and we can still get 150. And so this is interesting because it raises the possibility of doing DNP under operational conditions. So you're not suppressing things like dynamics that are maybe relevant for the process. So for instance, cerium oxide, when you dope with gadolinium, is an oxide ion conductor. And so if you want to look at oxide ion dynamics, you don't want to be down at 100 Kelvin. To sum up my first story, if you have these very symmetric crystals, you can get narrow EPR lines for high-spin metal ions, but you still become, there's still a limit, and in this case, you're limited by higher rank serial splitting. You do get some benefit though, and that arises from the rigid lattice, which slows down the electron relaxation. And so for gadolinium-doped ceria, we can get very large oxygen enhancements. We could do some cool stuff with that, which I didn't have time to talk about today, but happy to chat if anyone's interested. And what was quite nice here is we can apply this at room temperature or above room temperature, and we still get kind of appreciable enhancements. Okay, so moving on to story number 2. Oxygen is great. I love oxygen NMR, but it's not the most useful nuclei. Protons would be far more useful. The main reason here is that proton spin diffusion is very efficient. And so that means that you could relay your polarization through your sample, or from one part of the sample to another part of the sample, or possibly even outside of the sample to another phase. And so we wanted to see whether we could use these design principles to get endogenous proton DNP. So what we wanted was a material that contains protons and that has a highly symmetric metal site. And so while we were searching for such a material, came across indium hydroxide. And so indium hydroxide contains protons, 1 tick, and the unit cell is cubic. And so that was why we sort of started looking at it. So full disclosure, we probably should have done slightly more careful crystallography before jumping into this project, because even though the unit cell is cubic, the metal site is not. The metal site has bar 3 symmetry. And in fact, this is also the average symmetry. So you can see here that there's proton disorder, and that's going to also affect our metal symmetry, which we'll come back to. But in any case, this is why we were looking at this material. So the first question is, can we dope gadolinium into indium hydroxide? And so this is all work from a master's student in the group, Yushuan Zhang, who made this by hydrothermal synthesis. And so the first thing we did was to measure the proton relaxation. So pure indium hydroxide, shown in blue, the T1 relaxation. And for a sample with a nominal concentration of 0.1%, we get a significant reduction in the T1, the protons. So this is an example of paramagnetic relaxation enhancement. This is mono-exponential, or it's stretched, in fact, but it's at least a single component. And so this tells us that we have gadolinium doped in throughout the material. So this shows that we have incorporation of gadolinium. Of course, we also do the EPR. And so this is the X-band EPR spectrum. I would describe this as a sharp-ish signal. And so we've got a symmetric-ish site. But there are also sort of broader features, and this is a bit of a weird line shape as well. And so I guess kind of half marks in terms of the EPR, and that's something we'll come back to. The next question is, okay, we've incorporated some gadolinium, will it do DNP? So this is showing the proton spectrum, again at 100 Kelvin under magic angle spinning. Blue is microwave off, and red is microwave on. And so we can see we do get an enhancement. We get an enhancement of around 9, but that's quite a moderate enhancement. So again, comparing to a factor of 38 for the best organic complex. And so if we do a field profile, so here our microwave frequency is fixed and we're varying the magnetic field and measuring the enhancement at each point, enhancement epsilon. The factor of -1 is to account for the Boltzmann, the thermal polarization. And what you can see is we see 2 lobes that are separated by twice the Larmor frequency. That's characteristic of the solid effect. There are sharp-ish components at the lobes, but there's also a very broad sort of underlying profile as well. So this broad profile implies that we've got a broad EPR spectrum, sort of as we saw, And that's why it's harder to saturate and we're getting less efficient DNP. That said, we can still use this magnetization, this enhancement, to measure natural abundance oxygen now. So again, around 0.04%. So here we're taking the proton polarization, which is relayed through our sample, and then transferring it to oxygen using a Presto sequence. And then this is the oxygen spectrum recorded in about a day. And so given the enhancement of around 9, this would take 80 days to get comparable signal to noise without DNP. So this is already of use. We get a nice second order quadrupolar line shape, and we can fit that to extract the shift and the quadrupolar coupling parameters. Okay, now let's have a think about why we're not getting better DNP. And so as I alluded to earlier, this comes down to the proton disorder. So shown here is the metal site and the average coordination, which is roughly octahedral. But each oxygen has 2 proton sites, which have 50% occupancy. And so this obeys ice rules. So each oxygen has to have 1 covalent bond and 1 hydrogen bond. But there's 2 possible ways of doing that. And so each of these oxygens can have the proton in one of 2 positions. And so that means that we've got 64 possible nearest neighbor proton configurations about this metal. We have a random distribution of them. And importantly, most of them break the local symmetry. And so this will give rise to zero field splitting, and hence a broader EPR line. To test that, again, as someone who's not an expert in EPR, I mean, I'm sure one way to do this would be to go to higher field in the EPR. But I thought, why don't we use NMR to look at this? Because indium is a quadrupolar nucleus, and so it's subject to quadrupolar coupling, which is induced by a non-cubic charge distribution the same way as zero field splitting. So if you measure the indium spectrum, so I did this both under magic angle spinning and static at 2 different fields. And what you see is this characteristic line shape where we have this tail down to lower frequency. This tail down to lower frequency. And so this is characteristic of the distribution of quadrupolar coupling, and we can model this using a Čeček distribution. So a Čeček distribution basically assumes that you've got an electric field gradient where each component is normally distributed around 0, but because your quadrupolar coupling is always the biggest component of your tensor, that has a slightly different distribution. So basically this sort of distribution, we've got a distribution of quadrupolar coupling, which means we've got a distribution of second order shifts, and those second order shifts go out to negative frequency. So that's why it spreads out here. So what this means is we've got a random distribution of electric field gradients, giving rise to this distribution of quadrupolar coupling. If we come back to our EPR spectrum, where we also have this kind of funny tail to lower frequency or higher field, I wanted to see if we could kind of assign this to a Čeček-like distribution. And so to do that, I did a very rough integration of the peak. And again, this kind of looks Čeček-like. And then if you simulate this in easy spin with a Čeček distribution, you can more or less reproduce the sort of features you have there. So what we've learned here is that the distribution of electric field gradients can qualitatively explain the broadening of the EPR line, and the broadening of the EPR line explains the poor DNP. So with that, to sum up this little story, so this was the first example of proton DNP using endogenous gadolinium. So that meant that we could get a nice, we could get a proton DNP enhancement. We could use it to measure the natural abundance of oxygen. But of course, it's very important to consider the local symmetry, and that came out both in the indium NMR and also in that EPR line shape. Okay, so switching gears a little bit now, we're going to go from metal ions to bulk metals. And so this is interesting because dynamic nuclear polarization was actually first proposed and demonstrated in metals. So proposed by Overhauser in 1953, and then demonstrated a few months later by Carver and Slichter. And this was done in lithium metal. So this is a figure from that paper by Carver and Slichter. And so this is the lithium NMR spectrum without DNP. And then with DNP, you can see that there's a big boost in the NMR signal. Okay, so to understand how this works, I'm going to have a brief recap of what a metal is. So a metal has delocalized electrons in a partially filled band. And so we can consider, rather than up and down spin levels, we have up and down spin bands. We have an up spin band and a down spin band. If we put a metal into a magnetic field, our bands shift in opposite directions. So one's raised in energy and one's lowered in energy. But we still maintain a common Fermi level. What this means is we now have an unbalance of the unpaired spin density, and this generates a magnetization that augments the applied field. So it's worth mentioning here, my arrows here show the magnetization of these electrons, which is opposite in direction to their spin. Okay. So this is known as Pauli paramagnetism. We have an unpaired delocalized electron spin density that augments the applied field. And this is temperature independent, at least to first order. This is in contrast to Curie paramagnetism, which has a strong temperature dependence. So you can do EPR on those delocalized unpaired electrons. This is sometimes called conduction ESR. And so this is an example of lithium metal. It's not really something that I've done much research on myself, so I'm just taking data from the literature. If you have a small sample of lithium, you get a sharp Lorentzian line shape. Whereas if you have a bulk piece of lithium where the sample is bigger than the skin depth of your microwave radiation, then you get this distorted line shape, which is known as a Dysonian line shape. And so you can use the EPR to explore the morphology of lithium metal, whether you have large particles or small particles. These unpaired electrons are also coupled to your nuclear spins. And so this gives rise to something called a night shift. So it's the hyperfine coupling of the nuclear spin to the net delocalized unpaired electron spin density. First reported by Walter Knight in 1949. And for lithium metal, at least, we're dominated by s orbitals at the Fermi level. And so we get a direct contact night shift, which is positive. So diamagnetic lithium is around 0 ppm, but lithium metal is shifted out to around 260 ppm by this night shift. Okay, so how does DNP of metals work? Well, this is an example of Overhauser DNP, named after that original Overhauser paper. So now instead of driving the 0 quantum or the double quantum transitions with microwaves, we drive the single quantum electron transitions, shown in green. So most of those electrons will relax due by a single quantum relaxation, these red lines, but we can also get cross relaxation with a nuclear spin. And so this cross relaxation is going to result in a buildup of population on the left-hand side of this diagram if we're dominated by this 0 quantum relaxation. And that's going to hyperpolarize our nuclear spins, analogously to those population circles we looked at for the solid effect. The difference is, for Overhauser effect, we can't pick whether we have 0 or double quantum cross-relaxation. So for lithium metal, the hyperfine coupling is dominated by Fermi contact. This is an isotropic interaction, and so it can only drive 0 quantum cross-relaxation. So that means that if we have a positive gyrometric ratio of the nuclear spin, we get a positive enhancement. And so that's the case for lithium metal. Those of you who are familiar with the nuclear Overhauser effect will know we also need spectral density to drive this cross-relaxation, and in metals that comes from rapid translation of the electrons. And so that's why DNP works in metals. Okay, so this is very nice, but as I mentioned, this was already done 70 years ago. What I didn't mention is that work by Carver and Slichter was at very low field, so 3 millitesla, which means you have 50 kilohertz of NMR frequency and an electron frequency of 84 megahertz. That meant they could use radio frequency amplifiers to generate very high power saturation in order to achieve the DNP. What we wanted to do is see if this works at the high field systems that are necessary for high resolution NMR. And so fortunately, the progress we made in the last 70 years, we now have these high power gyrotrons that can generate high power microwaves at upwards of hundreds of gigahertz. So this is on a 263 gigahertz system, 9.4 Tesla. And what you can see is going from our microwave off spectrum in blue to our microwave on spectrum in red, we get an enhancement in our lithium NMR signal of lithium metal by a factor of almost 30 in this case. The other interesting feature to note here is this tail down to lower frequency. I realize that we've been talking about lots of different tails this talk, but this is for a different reason. So I mentioned that the night shift is due to coupling of our nuclear spin with the unpaired electrons in the metal. I also said in order to do Overhauser DNP, we need to saturate our electron transition in order to drive that cross-relaxation. And so this reduction in the night shift is actually due to the partial saturation of the ESR transition. What we can also see is that we're only saturating by maybe 10%. And so that also explains why we're not getting a larger enhancement. We're achieving rather small saturation. And again, that's because even with a gyrotron, we're limited in the microwave power that we can apply. Okay, so in Claire's group in Cambridge, interested in battery materials. And this project, we were seeing what we could use this lithium metal DNP for. We're interested in lithium metal anodes. And so these are interesting because they have the ultimate capacity. So in your phone at the moment, you'll have a graphite anode. So you're obviously diluting your lithium with carbon. So it has a lower volumetric and lower gravimetric energy density. Whereas lithium metal is the densest you can get lithium. The reason we don't use lithium metal is on charging, it forms dendrites. And these eventually short circuit your cell and it tends to then catch fire, which is obviously a problem. Now, we wanted to understand why we get nucleation of these dendrites. And it turns out this is due to lithium transport across the solid electrolyte interface, or SEI. So the SEI is a passivating layer that forms on the surface of the lithium metal due to breakdown of the electrolyte. And so this is a mixed organic, inorganic coating. It's heterogeneous. And you imagine that your lithium ions have to get through this in order to reach the metal surface and deposit this metal. And so if that lithium transport is heterogeneous, you're going to get hotspots, and that's where you're going to nucleate those dendrites. And so this is a very difficult system to study. And in particular, we want to study this interface between the metal and the SEI, because that's where the dendrites nucleate. And so we're trying to study a buried solid-solid interface. What we're going to do is going to shine microwaves on our sample, hyperpolarize our lithium, and see how that transfers into the SEI. And harness that DNP of lithium metal to probe the metal SEI interface. Okay, so let's see how that works. I'm going to zoom in now on the diamagnetic region of the spectrum around 0 ppm. And so again, blue is microwave off, red is microwave on. We see that the sharp signal comes from the liquid electrolyte. That's not enhanced because it's not in contact with the metal surface. Whereas these solid this broader component arises from solid components of the SEI, for instance, lithium carbonate, lithium hydroxide, and they are enhanced. They have an enhancement value epsilon above 1. And so that proves that they're in contact with the metal surface. So we've got spin diffusion from the lithium metal to these species in the SEI. We then looked at 2 different electrolytes. In particular, we looked at the effect of this additive fluoroethylene carbonate, which has been shown to give a more stable SEI. Here, the interesting thing is that we see different enhancements of different species. And so the species that have a larger enhancement relative to the other species should be closer to the metal surface. So we now use the relative enhancements to get spatial distribution through our sample. We're not limited to look at lithium. We can also transfer from lithium to proton by cross-polarization. And so this gives us some very broad signals that ascribe to polymeric species in the SEI, so the organic component of the SEI. Again, they're enhanced, so they have to be near the metal. And in fact, in this case, they're similar for both electrolytes. And we can also do fluorine. So if you do direct fluorine, you just get the PF6 anion in the electrolyte. Whereas, again, that's not enhanced because it's not in contact with the metal. Whereas if you do cross-polarization, well, for this sample, we don't see any signal, whereas with the added fluoroethylene carbonate, we now see a signal from lithium fluoride. Again, this has a larger enhancement than the other species. And so that tells us that it's closer to the metal surface on average than the other species. And so what we think happens is this FEC breaks down at the surface, it forms this lithium fluoride, and hypothesize that's what's giving a more stable SEI. Okay, so to sum up that final story, we can use DNP to enhance lithium metal, and the progress we've made in 70 years is we can now do this at high field. We can harness that hyperpolarization to selectively probe the metal SEI interface. We can extract the spatial distribution from the relative enhancements. And in particular, we see this lithium fluoride, which is close to the metal surface. And we think that is of relevance to understand the kind of electrochemical properties. So with that, I'd like to thank the various co-authors on this project. So work I did with Claire in Cambridge, with Lyndon at EPFL, and with various collaborators, including some people in the Driscoll group and Sage group. I didn't get a chance to talk about that work today. Thanks to the funding bodies, and thank you very much for your attention. I'm happy to take questions.
Thank you very much, Michael, for the brilliant talk. Both a very good tutorial for the DNP and also the introduction to the applications. We're now open for questions. I will start with one general question. So you mentioned that the spatial distribution of the nuclei can be exploited by using the DNP in the case of lithium metal, but in other cases, it will also cause the line broadening when you apply DNP. And is there a trade-off or like a rule that we should follow? So in which cases it would be better to use DNP, and in which cases it will not bring?
Okay, yeah, so there's a lot to unwrap there. One thing about line width. So it's entirely right that it's quite common to get broader signals in a DNP experiment than you'd maybe get in a room temperature experiment. That's typically because you have dynamics at room temperature that cause partial averaging of sort of anisotropy or distributions, which are then frozen out at 100 Kelvin, and so you get a broader line width. That can be the case with sort of biological samples, for instance. I would say it's worth remembering that that's not a general rule, and so there will be situations where you get very sharp lines at 100 Kelvin, often the case in inorganic materials which have less dynamics in the first place. So that's one thing. Talking about whether you can get relative spatial distributions. This is not the only example of that. And here I've done this quite qualitatively. I've just said it's bigger or smaller, so that means it's closer or further away. There's been a lot more sort of formal work in Linden's group and in others modeling spin diffusion. So typically focusing then on protons rather than lithium to get the distribution of different species in space. And so one example on sort of core shell nanoparticles, being able to actually use the DNP buildup profiles to extract the size of the shell on that core shell nanoparticle. So that's definitely possible in different sorts of systems, but I would say the analysis is quite hard. So comes back to when should you use DNP? I would say there's two reasons. The number one reason is when you need sensitivity to do an experiment that would just simply take too long to be possible at room temperature. And so there are lots of examples of that. Natural abundance oxygen is a nice example, just because there we're limited by sensitivity, just because we have a low natural abundance. Other nice examples when you have species present at very low concentrations, so that could be catalysts on a surface, which are present at low concentrations, drug molecules in a cell, these sort of things where you just have very, very low concentrations, especially if you want to then do multi-dimensional or more complicated experiments. Of course, there will be situations where the DNP doesn't help, but you probably have to look at a case-by-case basis as to when that would be.
Great, thank you. There's a question in the chat. You mentioned from Amrit Venkatesh. I'm not sure whether I pronounced correctly. You mentioned the species in the SEI are polarized by the spin diffusion. How fast are the lithium relaxation time on the electrode? Could there be direct DNP from the metal to the species present in the interface?
So the relaxation of the metal is fast. I'm not going to quote a number because I'll get it wrong, but qualitatively speaking, let's say fast, and the numbers are in the paper. But we're continually generating that polarization. So to a certain extent, it doesn't really matter that they're relaxing quickly, because they have a steady state polarization that's higher than the diamagnetic species in the SEI. So we do have evidence of spin diffusion. So we have XC spectra where we see exchange between the metal signal and the diamagnetic species in the SEI. Of course, that doesn't rule out any direct contribution that could be there, but we know from the sign of the DNP that it's dominated by Fermi contact, right? So Overhauser DNP with a positive enhancement means that we're dominated by Fermi contact, and you're not going to get significant Fermi contact between the metal and diamagnetic species in the salts. It's my, at least off the top of my head, that's what I would say.
Okay. Makes sense. Is there any other questions? I have another question about the radiation damping you mentioned very briefly.
Yeah.
Could you comment a bit more on how that affects the line shape of the EPRN?
Yeah, I took out these slides. There wasn't enough time to talk about it. So radiation damping is an effect whereby a large magnetization couples to the RF circuitry and induces a magnetic field that acts to rotate the magnetization towards plus Z. So it acts as an additional source of transverse relaxation. And so it just makes the line broader because it's the T2 relaxation is faster, or some sort of transverse relaxation. What was surprising in this system is if you imagine you generate negative polarization and it still acts to rotate it towards plus Z, you actually spontaneously generate transverse magnetization. So this is something known as the Raser effect. And we were actually able to, spontaneously generate transverse magnetization that behaves kind of chaotically. So there was a whole other paper on that effect that I didn't touch on, but there was some very interesting physics that just arise from the fact you have a very large magnetization.
Okay. So does that mean you don't need to apply RF pulse to see your energy?
Yeah, you don't need to. You just get and in fact, as long as you keep applying the microwaves, you actually reach a steady state. So you have steady state precession. So you have a signal that goes on for really as long as you care to measure it for. How useful that is in practice is, I would say, still open to debate, but there are people who are working on this for various applications, not in this system, but in other systems.
Okay. Okay, great. Thank you.
Michael, can I ask a simple question?
Please.
Yeah, it's a great talk. I really enjoyed your talk, okay? So my question is, I'm curious to know whether, if you remember like a semiconductor materials, sometimes there will be some kind of electron center or hole centers.
Mm-hmm.
That kind of materials, can we do some kind of DNP to characterize the semiconductor materials?
Yeah, it's a really good question. It is one that has come up a few times, and I would say I still don't have a very good answer for that. I would say in principle, yes, but probably you're going to be limited by the electron relaxation. And so I would say really the first port of call would be to see what is the ESR signature of the semiconductor, which I have to say I'm not sure about. And then you'd be looking at characterizing the electron relaxation to see whether DNP would really be possible. It's worth mentioning that this works really well in lithium metal. It doesn't work that well really in any other metals, and it's because lithium has the longest electron relaxation times for a metal. As soon as you have spin orbit coupling, you can get very, very fast electron relaxation, and then DNP becomes more or less impossible. I would say that. But it's an interesting idea. I'd love to see that.
Yeah, thank you. Thank you. My another question is like, say in the biology, okay, people use lithium carbonate for bipolar disorder in medical side, okay? But I'm not sure whether anybody look at some kind of lithium NMR as well as I'm just thinking, okay, maybe I may be wrong, but I'm just thinking because the lithium metals, like, lithium carbonate is used as a medicine for a bipolar disorder. Whether I'm just thinking whether we can do something with the DNP or something like,
I would say possibly not. Well, it depends what you look at. Again, so it wouldn't work for metal-based DNP because it's not a bulk metal in lithium carbonate. As to whether you need DNP just to see it, that would depend on the concentration, and I can't say I know sort of how concentrated lithium ions are in a biological system. I mean, 7-lithium NMR is reasonably easy as sort of NMR goes. The pitfall is really the fact that we have a very, very narrow shift range. So, every diamagnetic lithium salt is within around a ppm. And so actually getting discrimination and useful information from those diamagnetic systems is very difficult. So
thank you very much.
Thank you for your interest.
Thank you.
Is there any other questions? If not, let's thank Michael again. Thank you for the really nice talk. And we finished today's session, and we will see you next year already. So thank you.
Thank you very much for the invitation.
Thank you, Michael. Bye.